Okay, the other critical thing we have to add to the wind-forced response of the ocean is the asymmetry of the currents we get to see. Here we directly jump a few steps and write what is called a potential vorticity conservation equation, remembering that the capital D, capital DT is Lagrangian material or total derivative, which has partial time term plus the the divergence of the term, advection term. North source is sinks. So in for some special cases, the ocean conserves what is called potential vorticity. Why is it called potential vorticity? I like to use this kind of image to explain that. So this skater here is acquiring some rotation by stretching out, and then she can continue to change her rotation speed by simply changing her shape. By stretching out the legs and arms, she can slow down. By crunching together, she can speed up, and so on, right? So H here is the thickness between, let's say, two density layers of the ocean. As the water is moving around and the thickness of the layer changes, the rotation or the vorticity can change based on the thickness of the density layer. So that's why it's called potential vorticity, because she has certain vorticity she acquires, and then she can change it by simply changing H in that sense. Okay, so this is why it's called potential vorticity, because it can be locked up when the H is large, and it can be made faster when H shrinks. So zeta here is the relative vorticity, what we saw before as dV dx minus du dy, which we had seen. So zeta is relative vorticity. We can also call it curl, as we did for the wind stress when we did Sverdrup transport. And F is, of course, the planetary vorticity, or the Coriolis frequency, which locally at any latitude is 2 omega sine phi, which we didn't derive in detail, but you can find it in my other podcasts. And eta is often referred to as the absolute vorticity, so zeta plus F. Basically, if zeta plus F over H has to be conserved, then you can change zeta plus F by changing H, or by changing F, or by changing zeta, and that is conserved depending on how you move in response to what changes, right? So potential vorticity then is just absolute vorticity divided by some height or thickness of a layer. So Chris tries to explain western boundary intensification using this concept, and we already looked at the wind forcing and the gyre that gets set up. If you focus again on this part of the gyre where the Ekman convergence, wind-driven convergence related to the wind stress curl is pushing the isotherms down, is pushing the sea surface height up, then you expect that the gradient gravity-driven flow down the hill of a dome, which is the geostrophic flow, because the pressure gradient that is created by the gradient in the height of sea surface, remember eta d eta dx d eta dy that we wrote before. Of course, now we are calling eta as absolute vorticity, so you have to be careful. So the gradient, so let's say sea level height is the peak here. Water wants to flow down the hill, and then Coriolis is going to push it to the right, so you have flow coming towards you here as geostrophic flow. So just pressure gradient down the hill is balanced by Coriolis. By the same token, flow going here is pushed to the north by Coriolis, so you see the tail of the arrow here. So wind driven circulation is creating Ekman convergence and doming in the middle of the gyre, as seen by the high sea level here, and that is going to create geostrophic flow around it. Now we have to apply our vorticity conservation to it on this side and keep going towards the west to see how vorticity conservation gives us a narrow, strong current on this side. So imagine a water parcel moving on this side. Obviously it is going towards decreasing F, okay, which means if H is approximately constant in our potential vorticity expression, if H is approximately constant, if you decrease F to conserve zeta plus F over H, we have to increase zeta, which means the water parcel has to acquire a relative vorticity of the opposite sign. So F is decreasing, which means zeta has to increase, so it has to be in the positive Z direction. So that's what is shown here. So it acquires a relative vorticity in this direction, and that keeps accumulating as you go towards the west. So you have water coming to the south and water going to the north here, but as we said before, a lot of water is coming south and is acquiring positive relative vorticity, which means somewhere you have to move the water north and create negative relative vorticity. How can you do it? Obviously on this side you're going north, so F is increasing, which means relative vorticity must decrease if H is approximately constant, and hence you get compensating negative relative vorticity on this side to match the increasing F. Okay, it just turns out that this is spread over broadly, so there is a broad eastward current that is slow and shallow, whereas as you keep accumulating the relative vorticity, the compensating negative relative vorticity tends to happen in a very small frictional or inertial boundary current that is compensating and conserving mass by taking all the mass back north and by acquiring negative relative vorticity to compensate for the positive vorticity that is acquired by water parcels that are coming south. Okay, that's one way to explain it. Without math, this is always tricky. Another way to think about it is this way. So here we have strong western boundary currents, the Gulf Stream becoming North Atlantic current, the Kuroshio becomes the North Pacific current, and you have also the East African coastal current here, Somali current which changes direction because of the monsoonal forcing, East Australia current here, Brazil current here, and so on. And you have cold, broad eastern boundary currents like the Canary current, California current, Peru current, Benguela current, and so on. This region is different, as we said before, because the Indonesian through flow coming here is driving a coastal current that is in the opposite direction. You can see here there are cold currents, but here there is a warm current going south, and there is a West Australian current that is outside of this western boundary, Western Australian boundary, Eastern ocean boundary. Okay, so ignoring that, if you focus, let's say, on this, why do we have this? So the main thing to remember is that the winds can go around the world. They have no boundaries. They can go over the mountains and so on. So you have northeasterly trade winds and the mid-latitude westerlies pushing the water this way and this way. So you have a clockwise gyre, and you have to explain why these currents are narrower, deeper, and stronger than the eastern boundary currents. And the best way is to think again is curl your fingers around the winds, you get the sum going into the ocean, so there is a negative wind stress curl and relative vorticity being put into the ocean by the wind churning the ocean. And as I said before, the Coriolis is weaker here because it's closer to the equator, which is 0, and it increases towards the higher latitudes. So the Coriolis deflection is more here southward than is northward here, so there is a net southward transport of water, and there is negative vorticity being put in by the winds. So somewhere you have to move the water north so that water doesn't keep on coming south, so mass balance is required, and you have to create a vorticity of the opposite direction because you have negative vorticity being put in by the wind. So where can you do it? It turns out that you can only do it on the western boundary. So if you try to move water to the north in the eastern boundary, the frictional boundary will give you velocities, currents going to zero near the boundary, increasing towards the interior in the boundary current. So now if you curl your fingers in which way, if you put a paddle here, for example, which way would it rotate? It would be pushed faster on this side, slower on this side, so it will rotate this way. So you will generate more negative vorticity here. But if the frictional boundary current is on this side, then you have currents going to zero here, so you have the paddle turning this way, so you are producing positive vorticity to compensate for the wind stress curl putting in negative vorticity. Okay, so you can see which way the water has to move and see how the western boundary intensification is needed to balance the mass transport southward created by the wind stress curl in the Sverdrup sense, and also vorticity to compensate for the wind-driven vorticity to balance that. Okay, I think I missed the Sverdrup thing here. Yeah, sorry about that. So I had promised the Sverdrup stream functions. This is just early work in 1948 by Reed, which shows that he integrated df dy times v as required by Sverdrup model, beta v equal to curled tau. So he took the wind stresses, made some simplifying assumptions, and integrated this equation to show that in fact you can produce the observed circulation just using simple Sverdrup theory. And of course what you have to remember that this is a first order equation, so you can only impose one boundary condition. So you can only impose boundary condition at the eastern boundary to say there is no flow coming out and the stream flow has to go to zero. So you can see that the Sverdrup transport produces the subtropical gyre and the north equatorial and south equatorial current driven or wind driven equatorial gyre here, and it even produces the north equatorial and south equatorial countercurrents. Sorry, let's just focus on the northern hemisphere. So you can see that there is an equatorial circulation with the equatorial countercurrents and south equatorial current, north equatorial countercurrent, north equatorial current, and the clockwise gyre circulation, and so on. So remarkably, this simple steady state model, making so many simplifying assumptions, produces very realistic circulation given the winds. Okay, so that was the elegance and the beauty